The next layer of information in the NMR spectrum comes from peak areas. Peak areas are directly proportional to the number of protons, or to the relative numbers of protons, that give rise to that peak. What does this mean practically? I think this is best explained on an example. So if we look at the following compound, which has a methyl group, followed by a carbonyl, then another methylene group, oxygen, and then a T-butyl group. In this compound, we will have three different types of protons. We'll have this methyl group, which accounts for 3 protons, all these 3 protons will be equivalent to each other, but will be different from these two protons from the methylene group, as well as these 9 protons from the T-butyl. Within themselves, they're all equivalent, but they're not equivalent to any of the others. And so our NMR spectrum will have 3 peaks. The first one, probably the most showy one, will be those directly attached to oxygen. Then they will have those attached to carbonyl, the methyl group. And finally, we'll have the T-butyl group at the end. This is not drawn out to scale and might not correspond very clearly to an experimental spectrum, but what we will clearly see is that these 3 peaks have different areas underneath them. And measurements of this area and their comparison will reveal that this area will stand in the ratio of 2 to 3 to 9 to the other, corresponding to the 3 other peaks. And this will allow us now to go backwards and from these ratios determine the number of protons in a compound which correspond to them. These areas are often referred to as integrals or integration, because integration is basically the process of finding the area underneath some curve. And it's important to realize that these integrals really are areas underneath the peaks, not the peak height, because each peak has a certain height but also defined width, so it has a roughly triangular shape, and from that triangular shape these numbers can extract. The integration is typically provided automatically, and what we'll often see in an experimental NMR spectrum, go from 10 to, we'll see that we have the one trace for the peaks, for the actual absorptions, and then another trace for integrals. What I mean by this is that if we have an experimental NMR spectrum where we have several peaks, we will then have typically a thinner line which will be flat until it hits the first peak, and we'll have a little jump. It'll be flat again, and we'll have a larger jump here, and even larger jump here, and again a small jump here. And these distances in height, these are the integrals. And what we get out of these integrals is the relative ratio of areas corresponding to these peaks. This is another important thing that we need to understand, is that these integrals that we get from our integration, in this case this could probably be interpreted as 1 to 2 to 3 to 1, just give us the ratio. So we know that the ratio is 1 to 2 to 3 to 1, but this could very well be 2 to 4 to 6 to 2, or some even larger combination. So we have to be careful. Then the integration gives us only the ratio, not the absolute number of protons, but using some chemical logic and other pieces of information, we could very easily come to absolute number of protons. If we think about, well, what could this be good for, consider this. If we have this diisopropyl ether, on one side and the ethyl ether on the other, their NMR spectra to some extent will be largely similar, because we'll have this metal group. Well, both of them will have two peaks. Okay, one will come from the metal group, so it will be relatively shielded. The other one will be significantly de-shielded, because it will come from a group close to oxygen. Okay, so from that perspective, both the peak positions and the number of peaks should be similar. And if we're considering that this is an unknown compound, we will be a little bit lost until we look at the integration, and then we'll realize that the two peaks, these two peaks in the NMR of the diethyl ether will integrate for 6, while these two will integrate for 4. Here we will have the same ratio of 6 here, but 1 here. And so what we'll see experimentally will probably be 6 to 1 here, compared to 6 to 4, which will actually be noticed as 1.5 to 1 in this spectrum. But the difference at this point will be pretty clear, and we could pretty conclusively determine which one is which based on the integration of the NMR. So this is really where integration comes in very handy. The other piece of information which is much more general and comes out in a lot of other compounds is that if you have three-peak integration of 3, that oftentimes corresponds pretty unambiguously to a metal group. And the situation where you have integration of 3 coming out for some other reason are relatively rare. And once starting with that metal group, we can relatively easily establish the absolute numbers associated with other integrals and sort of move towards solving the structure. In the next subtopic, we'll present the last and the most complex piece of evidence that NMR provides us, that is peak splitting.